On this video, I'm going to briefly, I hope, look at completing the square and sort of start heading towards a few other things I'm going to do with quadratic relationships, parabolas in terms of graphing. So first of all, let's suppose we have a quadratic equation. Let's say x squared equals 100. It's obvious when you look at that x could be 10, and probably not as obvious until you think about it a little bit that x could be negative 10, because when you square a negative, you get a positive. We formalize that by use of what's called the square root property, which says that you could solve this equation by taking the square root. Now, the reason for the square root property is that technically, if you were to take the square root of x squared, although you might expect that the square root of x squared is equal to x, it actually isn't, because the one way of looking at this is the squaring function and the square root function are not inverse one another, because the squaring function technically doesn't have an inverse. And so if we take the square root of the square of x, what we'll get is x if it's positive and the opposite of x if x is negative. In other words, we get the absolute value. And so that would be equal to, in this particular case, 10. And then we're solving an absolute value equation that says the absolute value of x is 10. Well, there are two different values, positive 10 and negative 10, two different values that have absolute values of 10. Okay, so that's fine. Just have to remember that whenever you're solving a quadratic equation, that typically they have, if the exponent's 2, there are two solutions. This generalizes to polynomial equations, where if you have 3 as the degree of the polynomial, you anticipate the possibility of 3 solutions. Don't have to be 3, there has to be at least 1, but there doesn't have to be 3. For a quadratic, there do not have to be any real solutions, but the solutions often show up in pairs where you get 2 real solutions or 2 complex solutions. And in special cases, there's only 1 solution. All right, what we'd like to be able to do is to take this idea of taking the square root and generalize it. Well, you can actually do it in a lot of situations. Say we have 2x minus 7, that whole thing is squared. And let's suppose that's equal to, well, let's make it negative 5. So obviously the solutions are not going to be real here. If I take the square root of both sides of the equation, what we get is 2x minus 7. I'm not going to bother with the absolute value. We're just going to go straight to bring in plus or minus to deal with the fact that there are 2 different square roots of negative 5. Neither of those numbers is real. And then so what's traditionally written is, instead of what I wrote as plus or minus square root of negative 5, the typical way of writing this, again, the traditional way of writing it, is to bring in I, which is defined as the square root of negative 1, and then the square root of negative 5 is radical 5 times I. And then there's going to be another possibility by taking the opposite of that, negative root of 5i. Don't think too much about this, just note it. And it's really easy to get hung up on all the symbolism here and say, I don't know what's going on. Well, if you haven't seen this stuff before, you're not supposed to know what's going on. You just say, okay, I'll take your word for it and move on to the next thing. So we have this 2x minus 7 equals plus or minus radical 5 times I. Now, be careful about plus or minus in this situation, because sometimes assumptions are made which turn out to be incorrect. But if you have a situation like this where you're dealing with a radical term or a complex radical term like we have here, it's pretty common to go ahead and leave it the way I did with the plus or minus. Okay, so we have 2x equals, we'll add 7 to both sides, plus or minus square root of 5 times I. And then we can divide by 2, and we get x is equal to, different ways you could write this, 7, I'm going to write 7 halves plus or minus radical 5 over 2, that times I. So those are two different complex numbers that what are called complex conjugates by changing the, so we have a real part. The real part of this complex number is the 7 halves, so that's real. And then there's also an imaginary part. The real part is 7 halves. The imaginary part is radical 5 over 2, radical 5 halves, maybe. And if the imaginary parts are, the two numbers that have imaginary parts that are opposite of one another, plus radical 5 over 2 and minus radical 5 over 2, those are referred to as complex conjugates. And if you have a quadratic equation with real coefficients, ax squared plus bx plus c, where a, b, and c are all real, if that's the situation, then it turns out that if one complex number is a solution to the equation, then its conjugate will also be a solution to the equation, be the zeros of the function. Those correspond to x-intercepts in general, but in the case of complex zeros, it really means there are no x-intercepts. Okay, so what I want to look at is how you can use this technique to solve any quadratic equation, no matter what, and that's referred to as completing the square. So any quadratic equation can be written in the format ax squared plus bx, and I said it right and wrote it down wrong. I got distracted by things I should not be distracted by. X squared plus bx plus c equals 0. Any quadratic can be written out this way with the coefficients a, b, and c. They're going to be real numbers. A, b, and c will all be real numbers for our purposes. So for example, suppose we had 3x squared minus 7x plus 8 equals 0. Well, maybe initially we had the equation written out in some other way. You can always manipulate it. So maybe it was a 3x squared minus 7x plus 1 equals negative 7. Well, if you add the negative 7 to both sides, we're dealing with this equation where it's set equal to 0. Now, the key here is I'm going to make use of the fact that if you have some number, which we'll call x, and you add to that some other number, which I'll call n for number, if you go ahead and square that business, FOIL it out, and you get x squared plus twice the n times x plus the square of the n. And that's the key notion here. We change colors for this idea. Didn't change by much. We have two different things, 2n and n squared. So at the appropriate time, I'm going to make use of that to solve my equation here, 3x squared minus 7x plus 8. So I'm going to move on to a new screen, new whiteboard. So I can look at this. So again, it was 3x squared minus 7x plus 8. 3x squared minus 7x plus 8 equals 0. So I want to make use of that thing I had written down before, x plus n, the square of that. So to do that, I have to do some manipulation to this. So first of all, although the generic form of a quadratic has ax squared plus bx plus c equals 0. I'm going to rewrite this so that I just have the x terms on the left side of the equation. So we have 3x squared minus 7x equals negative 8. I'm going to add something to both sides of the equation, and the process of adding to both sides of the equation is referred to as completing the square. I'm getting a little ahead of myself here, because actually we have to do a little bit more manipulation before I get there. But completing the square. So when I was looking at it before, remember I had x plus something, square the whole thing, you end up with x squared plus twice nx plus n squared. Well, that means that here where I've got 3x squared, I really don't want the 3. So I'm going to rewrite this by dividing both sides of the equation by 3. You can also factor out a 3 in some situations, so there's variations on this. But if we divide by 3, we would have x squared minus 7/3 x equals negative 8/3. So remember the relationship. We had 2n and n squared. The negative 7/3 here is actually the 2n in my relationship. So negative 7/3, the coefficient of the x, and once I've got the x squared with the coefficient of 1, so we can have 1x squared here. The negative 7/3 is the coefficient, is the 2n that we're interested in. In which it follows that n is half of that, so that would be negative 7/6. And then the square of that is going to be, well, the squares are always positive, and the square of 7 is 49, the square of 6 is 36. So what I'm going to do is manipulate this. We have x squared minus 7/3 x plus, so again, I'm squaring 7/6, technically negative 7/6, but it's the same difference. We get 49 over 36. Add that to the other side of the equation, so we would have negative 8/3 plus 49 over 36. So the important thing with solving equations, of course, is to keep the equation balanced by whatever you do on one side of the equation, you do on the other side of the equation. Okay, so we have 49 over 36. To get to 36, I would have to multiply 3 by 12. So I'm going to also would need to multiply the 8 by 12 to do that. So what would that give me? Go ahead and write it like this. So we have, I'm going to write it as 49 minus 12 times 8 is what, 96, I believe. And then that would all be over 36. So 12 times 8 is the 96 here. That, of course, is a negative number. We'll come back to it in a moment. The important thing here is the left side of the equation, the left-hand side of the equation, is now the square of x minus, well, where did the 49/36 and the negative 7/3, where are those two things coming from? The 49 over 36 is the square of a number. The negative 7/3 is twice that number. And that number is what we're going to have here, which is the 7/6, or negative 7/6, maybe a better way of thinking about it, that was mentioned before. So x minus the square of 7/6 is equal to what you're seeing there on the right side of the screen, which works out to be, so 49 minus 96 is going to be the opposite of, so this is a negative number. And let me see, 96 minus 50 would be, it's not that hard to do, 46, so we would go ahead and have to add 1 to that to get 47, I believe. 47 over 36. I'm going to do a quick double check of my calculation here because I've been known to make mistakes. Okay, it looks right. Okay, so we have x minus 7/6, x minus 7/6. That squared is equal to the quantity negative, what was it again, 47 over 36. And then we can take the square root of both sides of the equation. We write this as x minus 7/6 equals, remember that plus or minus. Well, the square root of 36 is 6. The square root of 47 is the square root of 47. Remember, it's actually negative 47, and the square root of the negative brings in an I here. So even though the solutions involve both a radical expression, radical 47, and also this imaginary expression that we get by bringing I into it. If you're not familiar with I, don't worry about it right now. Just accept the answer, and maybe I'll do a video on complex numbers at some point here, but our solutions are 7/6 plus or minus radical 47 over 6, that times I. Those are two complex conjugate numbers. For graphing purposes, what these would tell us is that actually if you have the parabola equal to y, the parabola y equals, what did we start off with? Back up a few screens here. If you had the parabola y equals 3x squared minus 7x plus 8, well, it's never equal to 0 for any real number. So for graphing purposes, that would actually tell us that this parabola does not cross the x-axis. So it would have, you see the y-intercept is 8. And so probably something like that. I'm not going to worry too much about my sketch over here of the parabola. It's just very rough. Okay, so anyway, this was completing the square. Very important idea. We used it in college algebra all the time. And so if you're not familiar with completing the square, you should look at it in chapter 1 under solving quadratic equations, and maybe seek out some further guidance on that. That's it for this video. I'll pick up on this idea of completing the square and show how we can use that to find the vertex of any parabola.